So good morning students. Today I am going to discuss about reactions of glycolysis and also the metabolic effects of pyruvate. And we know what is glycolysis. It is a sequence where glucose is converted into pyruvate. One molecule of glucose is converted to two molecules of pyruvate with the production of ATP. And this sequence involves 10 steps. So let us know step by step what happens in step number 1. So in the first step of glycolysis, the glucose is phosphorylated to glucose 6-phosphate by utilizing one molecule of ATP. So D-glucose is converted into glucose 6-phosphate and ATP is converted to ADP with the help of the enzyme called hexokinase, which requires Mg2+ as an activator. So in the second step of glycolysis, it is an isomerization reaction where glucose 6-phosphate is isomerized to give fructose 6-phosphate. We have 6P. We know what are isomers. Isomers are the compounds having the same molecular formula but differ in their structural formulae. Here G6P and we have 6P are isomers. And this isomerization reaction is catalyzed by the enzyme phosphoglucoisomerase. And this fructose 6-phosphate then in the step number 3 utilizes another molecule of ATP and converted to fructose 1,6-diphosphate FDP. ATP is converted to ADP. So this is another step where ATP is consumed. This step is similar to step number 1. With the help of the enzyme phosphofructokinase, which requires Mg2+ and K+ ions as activators. And in the next step of glycolysis, that is step number 4, it is a conversion of fructose 1,6-diphosphate into glyceraldehyde 3-phosphate and dihydroxyacetone phosphate DHAP. So here 6-carbon sugar molecule splits into two 3-carbon sugars. One is glyceraldehyde 3-phosphate and aldose, and the one is dihydroxyacetone phosphate, a ketotriose. And this reaction involves carbon-carbon bond cleavage catalyzed by the enzyme called aldolase. So 6-carbon molecule gives 3-carbon sugar molecules, glyceraldehyde 3-phosphate and DHAP. So that is step number 4 of glycolysis. And in the step number 5, it is an isomerization reaction. All DHAP molecules gets isomerized to glyceraldehyde 3-phosphate. DHAP, a ketotriose, is isomerized to an aldose, that is glyceraldehyde 3P, 3-phosphate, with the help of the enzyme triose phosphate isomerase. So that is the enzyme required for the isomerization reaction. And in the next step, step number 6, it's an important step. We are entering into the second stage of glycolysis. Glyceraldehyde 3-phosphate is converted to 1,3-diphosphoglycerate. 1,3-diphosphoglycerate is a high energy compound other than ATP. By utilizing NAD+ and PI. NAD+ nicotinamide adenine dinucleotide and PI inorganic phosphate. So what happens in this reaction is the aldehyde group CHO group is oxidized to the level of carboxylate group. Then it is phosphorylated with PI to form 1,3-diphosphoglycerate. It is really called acyl phosphate. And during the reaction, NAD+ gets reduced to NADH and H+, catalyzed by the enzyme glyceraldehyde 3-phosphate dehydrogenase. That's the enzyme required for the formation of this high energy compound. And the importance of this reaction is NAD+ on reduction gives NADH, and NADH by oxidative phosphorylation through ETC yields 3 molecules of ATP. That is, one NADH molecule is equivalent to 3 ATP molecules. That is the importance. And here one more is we get a high energy compound, that is 1,3-diphosphoglycerate without the involvement of ATP. In the next step of glycolysis, that is step number 7, it's an important step. Another important step where 1,3-diphosphoglycerate loses one phosphate group, and this phosphate group is transferred to ADP to form ATP, and 1,3-diphosphoglycerate is converted to 3-phosphoglycerate. And this is the step where ATP is generated. ATP is produced with the help of the enzyme phosphoglycerate kinase with Mg2 plus as an activator. And this reaction is also called as substrate level phosphorylation. Then what is substrate level phosphorylation? Is the production of ATP molecule by the direct transfer of the phosphate group from the high energy compound to ADP in order to release and order to produce ATP molecule. So substrate level phosphorylation, it is a step where ATP is produced. And in this next step of glycolysis, that is step number 8, is an isomerization reaction where 3-phosphoglycerate is isomerized to 2-phosphoglycerate. The phosphate group at the carbon 3 is shifted to the second carbon. It is an isomer called 2-phosphoglycerate catalyzed by the enzyme phosphoglycerate mutase. Isomerization reaction. And in the next step of glycolysis, step number 9, 2-phosphoglycerate gets dehydrated. It loses a molecule of water, H and OH, to form another high energy compound, phosphoenol pyruvate, that is PEP, with the help of the enzyme enolase, which requires Mg2 plus an activator. So this is another high energy compound similar to 1,3-diphosphoglycerate, phosphoenol pyruvate. That is step number 9 of glycolysis. And in the last step of glycolysis, that is step number 1, phosphoenol pyruvate gives this phosphate group or donates this phosphate group to ADP to form ATP. PEP is converted to pyruvate, catalyzed by the enzyme pyruvate kinase, which requires Mg2 plus activator. So this is another step in glycolysis where ATP is generated, and this is the second substrate level phosphorylation in glycolysis. So you can summarize glycolysis in step number 1 and in step number 3. Step number 1 and step number 3. So these are the steps where ATP is utilized. And the step number 7 and 10, step number 7 and the last step of glycolysis where ATPs are generated. So step number 1 and 3, 2 molecules of ATPs are utilized. Step number 7 and step number 10, 4 molecules. There is a production of 4 molecules of ATP. So there is a net gain of 2 molecules of ATP per molecule of glucose, which is oxidized under anaerobic conditions. Okay, these are the reactions of glycolysis. Now let us discuss about the metabolic fates of pyruvate. So now let us discuss about the metabolic fates of pyruvate. What are the fates of pyruvate under anaerobic conditions in the absence of oxygen? And there are 2 metabolic fates of pyruvate under anaerobic conditions. One is formation of lactate and one is ethanol production. So that is, in certain cells, particularly in muscle cells and lactic acid bacteria, the product of anaerobic glycolysis is lactate, which is obtained by the reduction of pyruvate, catalyzed by the enzyme lactate dehydrogenase, LDH. And during the reaction, NADH gets oxidized to NAD+. So this is one of the metabolic fate of pyruvate, formation of lactate by the reduction of pyruvate. And another metabolic fate of pyruvate is production of ethanol. That is in yeast and in some other microorganisms. The product of anaerobic glycolysis is ethanol and carbon dioxide. Ethanol, ethyl alcohol and carbon dioxide. And this conversion occurs in two steps. So in the first step, pyruvate is converted to acetaldehyde, which is catalyzed by the enzyme pyruvate decarboxylase. And in the second step, acetaldehyde is reduced to ethanol with the help of the enzyme alcohol dehydrogenase. And here also NADH gets oxidized to NAD+. Pyruvate to acetaldehyde, acetaldehyde on reduction gives ethanol. So this is another metabolic fate of pyruvate. One is formation of lactate by the reduction of pyruvate, another one is the production of ethanol by the reduction of acetaldehyde. With the help of the enzyme, there are two enzymes are required, pyruvate decarboxylase and alcohol dehydrogenase. So in the next presentation, I will going to discuss about aerobic carbohydrate metabolism, that is conversion of pyruvate to acetyl-CoA and oxidation of acetyl-CoA through TCA cycle and energetics of TCA cycle. Okay. Thank you.